Hey, today I'm going to be talking about the phase equilibria of the polyatomic hydrocarbons that we determined using hybrid Monte Carlo with Wang-Landau sampling. This is a paper that we published a couple of years back. Just as an outline, first we'll talk about the motivation for my research. Why is it important? Why do we care? A little bit on the simulation methods. Talk about the actual HMC Wang-Landau method. Talk about the details for the pHs that we studied, and then how the results that we obtained numerically, how we could actually use those to get the values on the graph that we want. And then I'm going to talk about a little bit of the results, and then the applications and future work followed by conclusions. So the PAHs, or polyaromatic hydrocarbons, why do we care about those? Well, PAHs are produced during incomplete fuel combustions, and they're hazardous to human health. So if you're living next to a road, it's bad. You don't really want to be breathing in as much of that stuff. You don't want to be breathing in that stuff as much as possible. Therefore, it's important for us to determine their phase diagrams because it's a combustion process between liquid and vapor. So phase diagrams are very essential. It's also important to develop really effective methods for determining the critical parameters associated with these phase diagrams. So the pHs that we've studied are naphthalene, phenanthrene, and anthracene. Just going to talk a little bit about the simulation methods. First, I'm going to outline the problem. The problem is, currently out there, in order to effectively obtain the values that we want for this work, we need some sort of a uniform sampling that can sample all the different densities of the system, rather than just focusing in on the most probable locations. So a Boltzmann sampling will not work. What we need is Wang-Landau sampling. So here, if you just use a Boltzmann sampling, you can see following these Boltzmann distributions, these are much more likely. And the way our computational method works is, well, if you're just using regular Monte Carlo, the method works by, it would just be following through this, sticking to this Boltzmann distribution. And as you look here, this is the probability. So it's extremely unlikely to be able to cross this barrier between the two. So it's take a long time to get effective sampling, if even possible. So what Wang-Landau sampling does is it creates this flat histogram method. So it equally samples all of the various densities of our system. So before I get into a little more details of that, first I want to talk about these two flavors of computer simulation that we're involved with. Over here on the left, denoted by Oreo ice cream, the molecular dynamics. What that does is it follows the systems through time, through the various laws of physics and Newton's laws and that sort of thing. Over here on the right, we have Monte Carlo, which is more of a randomly samples the ensemble. So when you combine the two, what do you get? You get hybrid Monte Carlo, denoted by mint Oreo ice cream. That's much more tasty. So what this does is it replaces these random Monte Carlo moves with these little MD trajectories in the microcanonical ensemble. And this ensures that the system will be sampled effectively even at high densities. So it's basically allowing the system to relax a little bit and things can move much smoother. So there's two types of moves. First, I'm going to talk about the MD move. And what that is, as I explained before, it's just allowing the system to move and operate with the laws of physics. You can see it's just the configuration of the system's changing, the different velocities are changing, that sort of thing. And it's just, they're just bouncing around in this area that we have associated for it. And then this is the molecular dynamics move acceptance criteria. Second type of move, this is where the magic kind of happens with the Wang-Landau sampling method. What you have here is you have these volume changes. And what we have with our Wang-Landau sampling is the volume is changing throughout all the different densities. So we're keeping the number of particles constant, but because the volume is changing, the densities are changing. And it happens so that it randomly, actually it's not just purely random, but it's actually biased because of the Wang-Landau sampling, allowing for a flat histogram above all the different densities. So how this works is initially we set QNVT for 1 for all the different volumes. And this is dynamically updated after each of the moves, after each of the volume change moves, that is. And as the system goes along, it operates by this acceptance criteria. So if a specific volume has been visited more than another, then it's more likely to go to a volume that hasn't been visited as much. So then over enough time, pretty soon you have a nice smooth curve. You can see over there, if this works. Nope. So you have a nice smooth curve up there compared to this choppy curve right down the bottom. And the smooth curve showing that we have a converged estimate for our QNVT as a function of volume. So the potential models that we use for our PAHs, what we had to do is we originally started with this Buckingham exponential 6 potential when we had done work with this for a benzene. But because we're doing PAHs, we have naphthalene, and we have this little section of naphthalene, which is only carbon as opposed to just the CH section you can see over there when you're just working with benzene. So we needed some sort of a mixing rule to model the interactions. And so we implemented the Lorentz-Berthelot mixing rules. And this whole potential was published in our paper in 2010. And it's, I believe it's called the DHMD potential. Now, a little bit on how the results are obtained before I get into our actual results. Here we have the joint probability distribution with QNVT in the numerator, QNVT in the denominator, or in the denominator. And then QNVT here, the partition function can be obtained through QNVT. And then we can use this to find the least probable volume, which corresponds to the volume which is the energy barrier between the two phases. Once we have that, we can use that VB to obtain the saturation pressure, which is the pressure at which the two phases are in perfect coexistence. Once we have that, we can take the pressure of coexistence, you can see here in the exponentials, and it'll give us the density of the liquid, and in the same way we find the density of the vapor. And then through the density scaling allowance, we can find the critical temperature, which is what we're after. And then through the law of rectilinear diameters, we can find the critical density. Now I'm going to get into the much anticipated results, which was also in our paper. So here we have squares. It might be kind of hard to see, but here's the squares, circles, and triangles. So the squares correspond to naphthalene, and then anthracene and phenanthrene are the circles and triangles. Of course, they're really close because they're very similar sizes, just slightly misshapen from one another. And you can see the bolded figures are the estimated critical points and where there's critical temperature and critical density. Here's just some snapshots of our system just to kind of get a feel for what's actually going on inside here. We have, this is for phenanthrene at 750 Kelvin, so right around there. So this is at 0.07 grams per centimeters cubed. Over there is 0.18. You can see how it's noticeably different, and then if over there is 0.7 grams per centimeters cubed. So we're looking at right around that system, and the other two are right around here. This is just how the system will change as you do these random volume moves to ensure you have all the different volumes. So of course we can say our data is good, but if we don't compare it to experimental data, there's not really a lot of weight we can put on it. So here's some experimental. Our simulation is in the first columns for both the densities and the pressure over there. And then next to that is experimental values. You can see here we're extremely close for both the lower temperatures as well as the higher temperatures. And then over there the pressures are very nicely in agreement. This is all for naphthalene. So with that, I'm just going to talk a little bit of the applications that we're actually continuing on with this work. We're moving into these MOFs. What a MOF is this porous crystalline structure that contains both inorganic and organic phases. I'm not going to talk a lot about this because it's in another one of my talks, but I just want to talk about how we're applying the information we have obtained through this vapor-liquid equilibrium stuff into this newer research which we're working on right now. So these active sites, which are oriented by the inorganic sections, which in the case that we're working with is IRMOF 1 or MOF 5. You can see here those are the inorganic sections, and the organic sections, benzene dicarboxylate and you can see here that you have a lot of empty space inside of these porous crystals, so they can absorb quite a bit of substance, depending on the size of them off. Particular pH that we're working with is phenanthrene, and we're also doing naphthalene. And CO2 is kind of as a just to kind of test how the method works compared to other methods out there. But this is more in another paper, so I'll talk about that at a different time. So as for concluding remarks, what we needed some sort of a uniform sampling. So hybrid Monte Carlo was coupled with Wang-Landau sampling, and it worked very well, both effectively for time, how long it took to complete the simulation, as well as obtaining good values. These HMC Wang-Landau simulations were shown to be accurate and reliable for all the pHs we use. This can be readily applied to any different types of pHs, very, very large pHs, different shapes, different modifications, without having to apply any configurational bias or that sort of thing, so you save a lot of time there. And then this work was being applied to the work with our metal organic framework simulations, and so far that's going really well. With that, I'd like to thank members of my research group, Professor Delhamel, Dr. DeGrange, and another grad student, Andy Magnus, who is actually involved with this paper as well. And then the other members of my research group. Funding, of course, has been through Sunrise, NSF, and EPSCoR. And with that, I'd like to thank you all for listening.